Okay, so in this video we're going to start off by looking at 13.1, which is on page 610, okay, and we're going to be looking at radian measure. So up until now we've been looking at degrees for our inputs for our trig functions, and now we're going to move to radians. And the reason why we move to radians is because in calculus and in certain parts of physics we're going to want to use radians over degrees. So first off, radian measure of theta, so the angle measure theta, is defined as the ratio, not the ration, the ratio of the arc length S to the radius R. So I've written it here as theta equals S over R, and then you've also got it rearranged so that its arc length is equal to radius times theta, okay? And those are going to come in handy later on at the end of the first lesson. Another key thing to note is that 180 degrees is equal to pi radians, okay? So pi is equal to 180 degrees, and then we can rearrange that to solve for 1 degree is equal to pi over 180, and 1 radian is equal to 180 over pi. We're going to use those to help us convert our degrees in radians for the first part of the lesson. Okay, so in number 2, we are given 30 degrees and we want to convert this to radians. So we're going to use that first conversion because there's 1 degree in pi over 180 radians. So we're going to multiply by pi over 180. We can simplify. 30 goes into 180 6 times. So we get pi over 6. Okay, for 8, we're given negative 180. Again, this is in degrees, so we're going to convert to radians. So pi over 180. 180 goes into itself once, so this will be negative pi. The negative sign just carries through. And lastly, in 12, we're given 495 degrees. Again, we're going to multiply by our conversion rate of pi over 180. So then we can reduce this. 180... First, let's divide by 5. So this becomes 36, and this top becomes 99. 3 goes into each of these. We get 12 and 33. Another 3 goes into these, so we get 4 and 11. That can't be reduced anymore, so we get 11 pi over 4. That's our answer. Now let's go the other direction. So in the previous slide, we went from degrees to radians. Now we're going to go from radians to degrees. So we're going to multiply by our conversion. Before it was pi over 180. So to go from radians to degrees, we're going to flip it and multiply by 180 over pi. The pi's cancel out. 2 goes into 180 90 times. We get negative 90 degrees. Again, carry that negative sign through. For 20, we have 3 pi over 4. So again, we're going to multiply by 180 over pi. The pi's cancel out. 4 goes into 180 45 times. And so we get 3 times 45, which is 135 degrees. And lastly, let's look at 9 pi over 4. So we're going to multiply by 180 over pi. The pi's cancel. 4 goes into 180 45 times. 45 times 9 is going to be 405 degrees. Okay. The next part, we're going to bring in those formulas I mentioned before, so such things as theta is equal to S over R, and S is equal to R times theta, and R is equal to S divided by theta, okay? As well as the formula for area. Now this is where it gets a little tricky, okay? Area is, using this notation in red on the right, area is going to be 1/2 R squared times theta, or 1/2 R times S. Okay, so we can use either one to solve for our area. So in 52, we're given the arc length, which is 1.2. We're given theta, which is 0.5. And then they want us to find our radius and our area. So I want to find radius first because I need that to find area. So radius is going to be arc length divided by theta. So this is 1.2 divided by 0.5. And so we get 2.4 as our radius. And then to find area, we're going to do 1/2. I'm going to use the second one because I don't have to square anything. So it's r times s. This is 1/2, 2.4 times 1.2. And this is equal to 1.44. Okay. Now let's look at 54. R is equal to 8. Radius is equal to 8. Area is equal to 6. What is the arc length and what is theta? So remember, to find arc length, we need radius and theta. We don't have theta yet, but we do have the area. So we know that the formula for area is equal to 1/2. Let's use the first one, so r squared times theta. Okay, this has to be equal to 6 because they gave us area is equal to 6 at the very top. And what we're going to do is we're going to multiply both sides by 2 to move the 1/2 over. And then 8 squared, when we plug in our r, so we get theta is equal to 12 over 64, which is 3 over 16, or about 0.1875. And then to find s, that's equal to radius times theta. So s is equal to 8 times 0.1875, which is 1.5. Now let's move on to 13.2. This time we're looking at circular functions. So before we move on to circular functions, we're going to talk about the unit circle. The unit circle is exactly what it sounds like, okay? It is a circle with radius 1, as you can see by the formula I wrote on the screen. It also has a center of 0, 0. So whenever I say the unit circle, I'm referring to a circle with center 0, 0 and radius 1. And if you notice to the right of the screen, I've drawn that circle. Okay, so the radius here is 1, as you can see by that red line. It's a little fuzzy. And then what's so great about the unit circle is that with the radius being 1, we can define an angle theta between the x-axis and the radius. And that corresponds to a point on my circle. And that point is usually written as xy, right? But with the unit circle, we're going to write it usually as cosine theta and sine theta. And if you notice, cosine theta is the x value, sine theta is the y value, and our hypotenuse is always 1. Okay, so any triangle we draw from here on out, if we're dealing with the unit circle, the hypotenuse needs to be 1. So this then redefines our trig functions, just a little bit, not a lot. And they redefine as such. Sine theta is equal to y, cosine theta is equal to x for points that are on the unit circle. Tangent theta is equal to sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. Cosecant theta is 1 over sine theta, granted that sine theta does not equal 0. And secant theta is equal to 1 over cosine theta, again, only if cosine theta is not equal to 0. These are called circular functions because they use a circle, in this case, the unit circle. So let's look at number 2. We're given the point -5/13 and 12/13. So they gave us our x and our y, or in this case, our cosine theta and our sine theta. So what I've done in the image down below is I have drawn where the point would be. So it would be in quadrant 2, right? Because the x is negative and the y is positive. And I've drawn a line segment that would connect it with a radius of 1, because again, we are on the unit circle here. And I've labeled my sides. So the y value, or the vertical leg of my triangle, is 12/13, and the horizontal leg is -5/13. Using my new circular definitions, I know that sine theta is the y value, so that's 12 over 13. Cosine theta is equal to negative 5 over 13. Tangent theta is going to be the numerator of the sine over the numerator of the cosine. Cosecant theta is 1 over sine, so it's reciprocal. Secant theta is 1 over cosine, so that's the reciprocal as well. And cotangent theta is 1 over tangent, so this is negative 5 over 12. And there are our answers. For the last part of this lesson, we're going to be using the unit circle, but a unit circle that's fully fleshed out in the sense that all of the standard angles have been written with their point values, and so their function values. And so if you notice, standard angles on the unit circle are 0, 30 degrees, 45 degrees, and 60 degrees, and 90 degrees. And they all have radian values that correspond as follow. 0 is 0, pi over 6 is 30, pi over 4 is 45, pi over 3 is 60, and pi over 2 is 90. So you're going to see, if you ever see any of those radian measures, know that you are on the unit circle somewhere. Okay, so this picture right here is very helpful. I like that it's in color. I find that some people struggle to memorize the unit circle or to be able to have a working knowledge of it. If you feel like you're in that boat, don't fret. You can always put this on your note card. Okay, so if you look at the unit circle, we've got all of our standard angles written out here. We've also got each one's point values right there, okay? And it goes from quadrant 1 to quadrant 4. So it works just like it has been with our circular functions and our radian and our degrees and our trig functions in general, okay? So first off, let's look at x equals, at the example where our theta is equal to pi over 6. So I know from that image I just showed you earlier on the screen that pi over 6 is in quadrant 1. So I'm going to draw that. And not only that, but it corresponds to 30 degrees. And I know that the point value for my unit circle is going to be square root of 3 over 2 for the x and 1/2 for the y. So I'm going to write that on my triangle that I've drawn here on my coordinate axes. And then now that I've kind of filled in the blanks, I can figure out my trig function values. Sine of our theta is going to be 1/2. Cosine of our theta is going to be square root 3 over 2. Tangent of theta will be the numerator over the numerator. This is square root 3 over 3. Cosecant of theta is going to be 2. Secant of theta is going to be 2 over root 3, which rationalizes to 2 root 3 over 3. And cotangent theta is going to be root 3. Okay? So there are all our answers. For 5 pi over 3, let's quickly take a peek at the unit circle up here. If I'm looking for 5 pi over 3, I notice it's not in quadrant 1, it's not in quadrant 2, it's not in quadrant 3. In fact, it's in quadrant 4. It is right there. Okay, so looking at 5 pi over 3, I see I'm in quadrant 4, so I'm going to draw that. Circles around this way. Here we go. The point value for 5 pi over 3 is 1/2 for the x, negative square root 3 over 2 for the y. So I'm going to fill that in. So then sine of 5 pi over 3 is going to be negative square root 3 over 2. Cosine of 5 pi over 3 is going to be 1/2. Tangent of 5 pi over 3 is going to be negative square root 3. Cosecant 5 pi over 3 is going to be negative 2 root 3 over 3. And secant 5 pi over 3 is going to be 2. And lastly, cotangent of 5 pi over 3 is going to be negative root 3 over 3. And those are our answers. Lastly, let's look at negative 2 pi over 3. Okay, So this one's going to throw us a little bit off because if you notice on the unit circle image that I had on the last slide, there were no negative radian values, but that doesn't mean we cannot move in the negative direction. So let's quickly remind ourselves that to move in the negative direction, we move clockwise, right? Whereas positive direction is counterclockwise. So negative 2 pi over 3 would put us right about there in quadrant 3. Okay? Because if we converted this to degrees, negative 2 pi over 3 is equivalent to negative 120 degrees, which is between negative 90 degrees and negative 180, also known as negative pi and negative pi over 2. So now that we know where we're going, the slight issue is figuring out our trig function values because we cannot just use the image of the unit circle anymore. So what we're going to do is we're going to do what we did last section. We found a corresponding coterminal angle. So we're going to find another radian value that ends at the same place that our 2 pi over 3 does. So in order to do that, we're going to subtract by 360. So 360 minus 120 is 240. So this is 240, also known in radians measure as 4 pi over 3. Okay, so now that we have our corresponding, we can go off of the unit circle here, and we know that at 4 pi over 3, we've got negative 1/2, negative square root 3 over 2. So cosine of negative 2 pi over 3, because that's our angle we're using here, is negative 1/2. Sine of negative 2 pi over 3 is negative square root 3 over 2. Tangent of negative 2 pi over 3 is going to be root 3. Secant of negative 2 pi over 3 is negative 2. Cosecant of negative 2 pi over 3 is negative 2 root 3 over 3. And cotangent of negative 2 pi over 3 is root 3 over 3. And those are our answers. And that's the first lesson. So the classwork is due Monday for F block, Tuesday for C block, and this is page 610, 1 through 23 odd, 45 through 65 odd, and page 617, 1, 3, 9 through 14 all, and 17 and 18. This will be due at the end of the class period.